The world's largest telescope, a marvel in the Atacama Desert in the middle of the barren Atacama Desert in Chile, where life is nearly absent, a groundbreaking engineering project is under construction. Perched 10,000 feet above sea level on a mountain peak, this project will soon host the extremely large telescope, ELT, the world's largest optical telescope. Once completed, it will revolutionize our understanding of the universe, offering views 5,200 times sharper than the human eye and 15 times more detailed than the Hubble Space Telescope. This is no ordinary endeavor. The Atacama Desert, known as the driest place on Earth after Antarctica, presents unique challenges. Some areas here have never recorded a single drop of rain in history. Yet, this desolate location has been chosen for a project that could unlock the secrets of the cosmos. How can a telescope in such an inhospitable environment explore the farthest reaches of the universe? Why the Atacama Desert? The Atacama Desert stretches over 1,000 kilometers along the Pacific Ocean in South America. It is a landscape of extremes, salt flats, volcanic terrain, and vast stretches of arid land devoid of vegetation. Yet, it is also uniquely suited for astronomical observations. One critical factor is light pollution, a major obstacle for ground-based telescopes. The Atacama Desert is remote, with no nearby cities to interfere with artificial light. Additionally, the desert enjoys exceptionally clear skies, with 320 cloudless nights a year. This combination of minimal light pollution and consistently clear skies makes it one of the best locations in the world for stargazing. The specific site for the ELT is Cerro Amazonas, a 3,000-meter, 9,842 feet, high mountain. While its elevation minimizes atmospheric distortions, the mountain itself posed a significant engineering challenge. Unlike flat terrain, Cerro Amazonas had a sharp peak, making it unsuitable for construction. Preparing the site to create a foundation for the telescope, the mountain's summit had to be leveled. Engineers began by blasting away 100 meters of rock from the top using explosives. This removed 4.7 million cubic meters of material, enough to fill 1,911 Olympic-sized swimming pools. The process took years and required careful planning to ensure the site could eventually support a massive structure. However, this was only the beginning. After the summit was flattened, engineers faced another problem: sinkholes. The use of explosives had destabilized the mountain's core, causing the ground to collapse in certain areas. Each time a sinkhole appeared, the team would fill it, only for new ones to form. The solution came in the form of artificial stabilization. Engineers drilled deep into the ground and used vibrations to trigger controlled collapses, allowing them to fill and stabilize the sinkholes permanently. This innovative technique took several more years but ultimately created a stable foundation for the telescope. The telescope's structure, the ELT, will feature a primary mirror with a diameter of 39 meters, making it the largest optical mirror ever built. This mirror is capable of capturing 100 million times more light than the human eye. To protect it, the telescope will be housed inside a massive steel dome weighing approximately 6,000 tons. The dome itself is a marvel of engineering. It stands taller than the Leaning Tower of Pisa, and is wide enough to fit an entire football field inside. Two massive doors on the dome can open to allow the telescope to observe the night sky. The dome can also rotate 360 degrees, enabling the telescope to point in any direction. Given the seismic activity in the Atacama Desert, the dome and the telescope's foundation are equipped with hydraulic shock absorbers. These devices can absorb the energy from earthquakes, preventing damage to the telescope's delicate instruments. Innovative technology at the heart of the telescope's extraordinary capabilities is its adaptive optics system. When light from distant stars travels through Earth's atmosphere, it gets distorted, creating a blurry image. To counter this, the ELT will use powerful lasers to create artificial stars in the sky. These stars serve as reference points, allowing the telescope's systems to measure atmospheric distortions in real time. Once the distortions are identified, the telescope's mirrors adjust themselves with incredible precision to correct the image. This process, called adaptive optics, ensures that the telescope can capture clear and sharp images, even from light years away. The primary mirror of the ELT is composed of 798 hexagonal segments, each perfectly aligned to function as a single unit. Light collected by the primary mirror will bounce through a series of secondary and tertiary mirrors before reaching the telescope's instruments for processing. Unlocking the universe's mysteries, the ELT's powerful optics will allow it to study some of the most profound questions about our universe. One of its primary goals is to search for exoplanets, planets outside our solar system. By analyzing the light from these distant worlds, scientists can determine whether they have atmospheres, water, or even conditions suitable for life. Unlike current telescopes, the ELT will be able to directly image exoplanets. This is a monumental achievement, as most exoplanet discoveries so far have relied on indirect methods, such as detecting the gravitational wobble of a star. Beyond exoplanets, the ELT will also look back in time. Light travels at a finite speed, meaning that the farther away an object is, the older the light we observe. The ELT will be capable of capturing light from galaxies formed just 300 million years after the Big Bang. This makes it an invaluable tool for studying the early universe and understanding how stars, galaxies, and planets came into existence. The cost of ambition